Hello students, I hope all of you are enjoying your studies and growing every day. Dear students, don't you feel that the nature is beautiful? The natural phenomena occurring in the nature are exciting. We feel happy when we see the twinkling stars. Right from our childhood, we love to hear the poem, nursery rhyme. Twinkle, twinkle, little star, how I wonder what you are. Every clear night, the sky is full of twinkling stars. All of us love to watch it, isn't it? When the sun rises, we see the red color of the sun. Slowly, the red color changes into yellow, and in the evening, during the sunset, again the color becomes reddish. The color of the sky, sometimes it appears to be blue in color, and the other time it appears to be white in color. What is the physics behind all these phenomena? In this topic today, we are going to know about the physics behind the apparent position of the star, the twinkling of the stars, the planets, why planets do not twinkle, the advanced sunrise and delayed sunset, the light scatter, giving rise to the Tyndall effect, the red color of the sun at sunrise and blue sky at the noon, the red color of the danger signal. First, let us understand what atmospheric refraction is. Atmosphere. All of you know, atmosphere is the cover of air around the earth. Let us see how this air is placed. If this is the earth, we see different layers of the air. The air close to the earth is greater in density. As we move up, the air becomes rarer. Because of this, the light entering the atmosphere bends, undergoes refraction, and this phenomenon is known as atmospheric refraction. First phenomena is the apparent position of stars. The actual position of stars is different from as seen in the sky. This is because the starlight bends from its original path due to atmospheric refraction. Now here, the star present at position A is not seen by us at position A, but it is seen by us at some other position, position B. Why does this happen? This is because when the starlight leaves the star and enters the atmosphere, it bends. You can see this is a normal. The starlight is bending towards the normal because it is entering a denser medium. Remember, as we move downward, the density of the air keeps on increasing. Again, at next layer, the starlight again refracts and moves towards the normal. At next position, again it moves towards the normal and takes this path. The observer sees the starlight, and because the light travels in a straight line, he knows that light travels in the straight line, he thinks that the star is actually placed over here. So, bending of starlight due to change of refractive index of the layers of the atmosphere is the cause of the apparent position of stars. Here, you can see the actual position of the star. Refraction takes place in the atmosphere and the apparent position of the star is seen. To the observer, he sees the apparent position, not the actual position of the star. Next phenomena is the twinkling of the star. Why do stars twinkle? Again, the Earth's atmosphere has pockets of warm and cold air. Because of these pockets, the light that's coming from the stars keep on changing its directions, and as a result, a flickering is observed. The light that enters the observer's eye keeps on flickering, and this gives a twinkling effect. So, as the path of the rays of light coming from the star goes on varying slightly, the apparent position of the star fluctuates and the amount of light entering the eye also flickers. This gives the twinkling effect. Both the reasons, that is the apparent position of the stars and the twinkling effect of the stars, is the result of atmospheric refraction. But why don't the planets twinkle? Don't they face atmospheric refraction? There is another reason. The planets are much closer to the Earth and thus they are seen as extended sources. Now what does these extended sources mean? Extended sources mean that a large source of light. Now if we consider a planet as a collection of large number of point-sized sources, it becomes an extended source. And as a result, the total variation in the amount of light entering our eye from all the individual point-sized sources will average out to be zero. Therefore, the twinkling effect is nullified. This is the reason why planets do not. The next phenomena that we are going to know about is the advanced sunrise and the delayed sunset. Due to the phenomena of atmospheric refraction, the sun is visible to us before the actual sunrise and after the sunset. The density of the atmospheric layer varies with altitude and hence the refractive index of the atmospheric layer also decreases. And as a result, what happens? Atmospheric refraction takes place. Here in this figure you can see the sun is below the horizon at point S, but it appears as though it has reached the point S1. Let us see what happens. The sun is below the horizon. You can see the sun below the horizon. Here, this is the horizon, and as it moves close to the horizon, the light from the sun reaches the atmosphere and starts refracting. That is, it starts bending. And because of this, its position appears as though it has reached above the horizon. That is, it has already risen. So, I am 2 minutes early. The sun is visible to us about 2 minutes before the actual sunrise and about 2 minutes after the actual sunset because of this phenomena, that is the atmospheric refraction. So students, I think now you have come to know that the Earth's atmosphere is not uniform. It is a heterogeneous mixture of minute particles. These particles include smoke, tiny water droplets, suspended particles of dust, and molecules of air. When a beam of light strikes such fine particles, the path of the beam becomes visible. The light reaches to us after being reflected through these diffused particles, and the phenomena of scattering of light by the colloidal particles give rise to Tyndall effect. You can see the Tyndall effect. To understand Tyndall effect, have a look at this activity closely. Here in this activity, we have two beakers, one filled with true solution and the other with colloidal solution. What happens when the torch throws light on the two beakers? We see when the light falls on the two beakers, the path in the true solution is not visible, but the path of light is visible in the colloidal solution. This effect is known as Tyndall effect. Now why does this happen? Why the path is not clear in the true solution but clear in the colloidal solution? The reason behind this is that when the light falls on the colloidal particles, they get scattered. Scattered means they get reflected. The reflected light comes into our eyes and make the path visible. All the particles in this path are reflecting light into our eyes and thus we can see the path. The same effect is known as Tyndall effect. This effect is very common in our daily life. You can see when light enters a dark room from a window, a beam of light, it is clearly visible. But when the light is full in the window, from the window it's not visible. Here you can see the light. All the suspended particles in the room become visible and thus the path also becomes visible. This effect is known as the Tyndall effect. In the atmosphere, you can see the Tyndall effect by the scattering of light by smoke and colloidal particles. You can see how the light is clearly visible when it passes through the atmosphere. Here, in the dense canopy, you can see the beams of light scattered by the colloidal particles like dust, mist, etc. present amongst the cluster of trees. The next phenomena that we are going to know about is why the color of the sky is blue. To know this, first we should compare the wavelengths of red and blue light. You know, the sunlight is made up of 7 pure colors. Blue at one end and red at the other end. The wavelength of the red light is quite large. We can see here. Whereas the wavelength of blue light is very small. This length is known as the wavelength, length of one wave. Here the length of the wave is quite large. The color of the scattered light depends upon the size of the scattering particle. Very fine particles scatter mainly blue light, while the particles that are large in size will scatter longer wavelengths. If the size of the scattering particles is large enough, the scattered light may even appear white. Now, why is the sky blue? The scattering of the blue light by gas molecules in the atmosphere can be seen in this diagram very clearly. As sunlight is made up of all colors, but the atmosphere mainly scatters the blue color. Why? Because the particles in the atmosphere are very minute. Tiny gas molecules that make up our Earth's atmosphere scatter the blue portion of the sunlight in all directions, creating an effect that we see as a blue sky. The next phenomena that we are going to know about is the color of the sun at sunrise and sunset. Why does the sun appear red while rising and setting? Within the visible range of light, the red light waves are scattered the least. Why are they scattered the least? Because they have longer wavelength. So at sunrise, when the sunlight travels a long path, the sun is present at this position during the sunrise. So it has to travel this long distance while the sunrise. Now when the light coming from the sun has to travel this distance, what happens over here? Here blue light scatters away, blue light scatters away, blue light scatters away, and the color finally reaching the observer that is left is the red light. So the sun appears to be red. What happens at the midday? The distance to be covered by the light is very short, and as a result, all the blue light is still not scattered away. As a result, the blue light is not removed completely, and to our eyes, the sky appears. So students, basically scattering of light is responsible for the blue color of the sky and reddish appearance of the sun at sunrise and sunset. What actually happens? Light from the sun near the horizon, you can see in this figure, it has to travel long distances. It has to travel through thick layers of the air. Because of these two factors, what happens? When the light is entering the atmosphere, the blue color that has short wavelength is scattered away. No blue light is left here. So when we see the sun, only the light coming from the sun left is the red color. Therefore, it appears reddish in color at sunrise and sunset. But when we have to look at the sky, what we see? We see that light that is scattered away. We are not looking at the sun, we are looking at the sky. So the sky appears blue in color. So I hope you have understood why the sky is appearing blue and why the sun appears reddish at sunrise and sunset. Both the phenomena are because of the scattering of light. The last phenomena that we have to know about is, why are the danger signals red in color? Again, red is used for stop signs, danger signals, because it has longer wavelength, so it does not get scattered easily, and it can cover long distances, thus reaching a far observer in case of a traffic signal or as a danger signal. And also, red color is the most visible color in all weathers: rain, dust and fog. So stop signals are red in color to avoid accidents, because red color is of a longer wavelength, so it can. Quickly we will recapitulate what we have learned today. First, what is the phenomena behind twinkling of stars? Is it atmospheric refraction, scattering, dispersion or Tyndall effect? I hope all of you know it is atmospheric refraction. The phenomena behind advanced sunrise and delayed sunset is again the atmospheric refraction. The danger signals are red because dash of the red color is more. Is it frequency, wavelength, time period or speed? It should be wavelength. The sun appears red during sunrise and sunset because of dash of light. Should it be dispersion or scattering? Should it be refraction or reflection? It should be scattering of light. And the last one, the optical density of the atmosphere is homogeneous, heterogeneous, exogenous or endogenous. Of course, it is heterogeneous. And because of its heterogeneous nature, all the different phenomena are occurring. I hope all of you have understood the topics, and if at all you have any doubt, you can contact me. I am Premlata from KV3 Jalandhar Cant, and if you don't understand, you can see the video again and again. Have a wonderful day. Okay, thank you so much.